All right, we went on a little tangent about speed and velocity, but I really wanted you to understand what that was before we finished customizing our equation. And this is what we've been doing this whole time, trying to get this equation, so let's get back to that. So the slope represents this idea of velocity, which tells us both how fast an object is moving and in which direction it is moving. So we can replace our variable for slope with the variable for velocity, a v with a vector arrow on top of it. And we did it! We just turned our equation for any boring old line into an equation that specifically represents the motion of an object moving at a constant velocity. Yay! This is what we've been trying to do the whole time. Get this equation right here. This is the most important equation of the summer assignment, and that is why we just spent 20 minutes trying to get to it. So this equation is our last way to represent the motion of an object. This is an equation that we can use to describe where an object is located, when it is located there, if it is moving at a known velocity. Notice it's the same equation that we just derived together. It's just standard to put the term for initial position first, so I just swapped these two terms. Also, fix this in your notes. I made a typo. Make sure that the velocity variable has a vector arrow above it because it is a vector. And make sure that the time variable here represents a time interval. It's delta t, not just a plain old t. So this equation directly connects to our graphical representation. We can go from one to the other because the initial position shown here is the y-intercept of the graph and the slope of the line is the velocity of the graph. So if you're given a graph of position versus time, you should be able to generate this equation by basically doing what we did in this experiment, finding the slope of the line and finding the y-intercept. You should also be able to do the opposite. If I give you this equation, you should be able to sketch what the graphs look like based on the fact that we will immediately know where this graph starts and the slope of the line continuing forward. So keep that in mind. This equation directly relates to our graph. But we can also use this equation to analyze a real-life situation, like a word problem or our actual experiment. This mathematical representation represents real things in real life. And here's what these variables represent. x0, this first variable here, is the initial position of the object. That is where the object is located at the start of our problem, at the start of the time interval. V with our vector arrow is the velocity of the object, how fast it is moving and in what direction. And in this equation, we can just use positives and negatives to show if it is moving left or right. Delta t is the time interval, or how long this motion is lasting, or how long we want to look at it over. So say we want to look at 3 seconds of motion, the time interval would be 3 seconds. And this x here is a different position than this one. Notice it doesn't have a subscript. This is the position at the end of the time interval. X sub 0 is the initial position at the beginning, and then this position is the position after all this time has passed. The position has likely changed. And I like to show this on a motion diagram type thing as well. So let's say we have an object that starts with an initial position of -8 meters. That's where it starts. And it is going to move to the right with a certain velocity. And we are going to let it do it for a certain amount of time. Well, this dot is going to move further and further to the right, to the right, and to the right until eventually our timer has stopped and the object is going to end up in a different position. And this is the phenomenon that this equation really represents. It's saying we're starting in one location, we're moving at a velocity for a specific amount of time, and we are then able to predict where this object is going to end up. So let's look at an example. I don't think I put this in your notes, but it's a standard physics problem. This is actually, I think, our first physics word problem. A car starts at a position of 10 meters. It then drives at a velocity of 5 meters per second to the right for 8 seconds. What is its final position? Where is it located after driving for those 8 seconds? So we are going to use our mathematical model. Although in theory, we could also create a graph of this. We could draw a motion diagram. We could solve this in many ways, but let's get practice with our equation. So our initial position is 10 meters. It says it starts at that position, so we can interpret that as our initial position. Our velocity is 5 meters per second, and since we are moving to the right, we're going to call that positive 5. And the time interval we care about is 8 seconds. This motion lasts for a time interval of 8 seconds. We are solving for the final position, so we're going to leave that as the variable. So from here, we're kind of done with the physics. We kind of just need to do some math. So 10 meters plus 5 meters per second times 8 seconds will give us 40 meters. Notice the seconds cancel out, and we're left with a position of 50 meters. The object has moved a total of 40 meters away from where it started at 10 meters, so its final position is 50 meters. All right, deep breath. I know we have done a lot in this section of the notes, but this was really the huge chunk of this chapter, was looking at these graphs and getting to this huge equation. But since we kind of got a lot of information from these past 3 or 4 pages of notes, I've given you this summary page. These are the big ideas, the big things that you really should have gotten from this section about constant velocity. So the first thing, big idea, objects can move with a constant velocity. This means that they move the same displacement each second. Their speed does not change, they're just chugging along nice and constant. And if we can visualize this by marking their position every second on a motion diagram, if we do that, there will be the same distance between each position. In each second, they travel the exact same distance. That is what constant velocity means. If you travel 4 meters in the first second, you're going to travel 4 meters in the second second, and you're going to travel 4 meters in the third second. You're going to do it forever and ever. The second big thing that we discuss is this idea of velocity. It's how fast an object is moving in a specific direction. We can find velocity by doing the displacement of an object divided by the time interval it took to do that displacement. Basically, how many meters it covers in how many seconds it took us to get there. Meters per second. We also looked at position versus time graphs, and motion at a constant velocity will show up on a position versus time graph as a straight line, a linear trend with a nice constant slope. So if you ever see a straight line on a position versus time graph, you know that object is moving along with a nice constant velocity. And we worked out that the slope of a position versus time graph represents the object's velocity. The slope will give you a steepness and a direction, positive and negative. We can use both of those to describe the velocity. And the y-intercept represents the object's initial position. And these two things led us to this key equation here that also allows us to describe the motion of an object, and we can use it to predict where an object ends up. Now here's the big thing. If you notice on this page, we have 3 different representations of velocity. We have our equation. Velocity is displacement divided by a time interval. We know that velocity is the slope of a position versus time graph, and velocity shows up in this equation here. We technically have 3 ways to figure out the velocity of the object. When you are asked to find velocity, you have to choose which one is relevant to the problem. If we know displacement and time, probably the equation here. If we know, say, initial and final position, I would use this one here. And of course, if you're given a graph, this equation is not as helpful. I would just find the slope of your position versus time graph. So we have 3 different ways to represent velocity. In the quizzes that I'm going to post, make sure you choose the correct one. Don't think, oh, I have to find velocity, I automatically have to use this mathematical definition. That's not always true. You're not always going to just plug in displacement divided by time. This is not a cure-all, use-all for velocity. You have 2 other representations that we can use to find the velocity of an object. So keep that in mind as we go into our practice problems and as you take your quizzes. So I have 3 pages of practice problems for you. These show up on pages 38, 39, and 40 in your notes. Some of them involve math, some of them involve graphs, some of them involve describing things in words. What I want you to do, take some time, practice these things, and look at the solutions that I have posted. If a lot of people are having a lot of trouble and I get a lot of emails, I might make videos explaining them, but hopefully the little notes that I add to the solutions will be helpful. So take some time, take this big idea summary sheet, really rewatch the videos if you need to, but try to work through the 3 problems, 38, 39, and 40, those 3 pages in your notes. If you're able to do those, that will definitely help you with the quizzes that I have posted. And to be honest with you, what we just did in this series of videos is very complex. This was a very complex idea that we needed to work through, going from this experiment to our graph to our equation. So if you're feeling a little overwhelmed, this is the hardest thing that we needed to do for the summer assignment, which is why I've spent about 35 minutes going through this idea of just getting to this basic equation. So feel free to go back and rewatch the videos, get the lecture again, slow it down. But just as a reminder, this was probably the hardest idea that we had to get through, working through these last 2 representations of motion. And we're going to get lots of practice with this idea, all of these different ways to represent motion at a constant velocity. But use your notes, make sure you understand all the words that were written down, go back and rewatch the videos until you feel really confident with this idea. I will see you in our last video, which is actually super short. Graphing velocity is pretty easy. Then we'll be done with the summer assignment. So we are almost there. See you in the next section.